Large language models are, well, they're truly everywhere, aren't they? Constantly amazing us with what they can do. But there's this one big, persistent challenge that keeps popping up, hallucinations. You know, you've probably heard the term, LMs just making up facts or confidently stating things that are flat out wrong. Sounds almost like science fiction, but it's a very real and pretty significant problem in the AI world. Today, we're diving deep into some fascinating new research from Google DeepMind, specifically their paper called Training Language Models on the Knowledge Graph, Insights on Hallucinations and Their Detectability. And this study, it really goes right to the core of what hallucinations are, and maybe more importantly, how they behave as these models get bigger and bigger. So what's our mission for you today? Well, we're going to explore exactly how these researchers managed to get a handle on such a slippery problem. We'll unpack some surprising trade-offs they uncovered when trying to reduce hallucinations, and why even the most advanced LMs might actually be getting better at hiding their mistakes. Get ready, this might challenge some of your assumptions about AI reliability. All right, let's kick things off by grappling with the fundamental challenge here. When we talk about hallucinations in LMs, it's actually incredibly difficult to pin down what that means in the real world, with messy natural language. How do you definitively say an LM is making something up versus just like stating a fact it learns slightly differently, or maybe a less common but still valid interpretation?
Precisely. And that brings up a really tough question for researchers. If you don't know exactly what information a model saw during training, how can you tell if an output is wrong because it never learned the fact? Or maybe it just didn't memorize it correctly, or maybe it learned something incorrect in the first place. This is where the researchers in this paper got really quite clever.
Right, and this is where it gets super interesting. They use something called a knowledge graph, or KG. Now picture this. Instead of the usual vast, kind of chaotic ocean of text data LMs normally learn from, imagine a perfectly organized, highly structured database of facts, just pure facts. And every single piece of information is broken down into simple subject, predicate, object triplets, like Sergey Brin, inventor of Google, or maybe TensorFlow, software and genre machine learning. Simple as that.
Exactly. And what's so, well, revolutionary about using a knowledge graph here is the complete control it gives you over the factual content. Unlike natural language, where the same fact might pop up loads of times with slight variations or, ambiguous phrasing, in a KG, you can definitively check, does this generated fact actually exist in the training data set? Yes or no? This gives you a quantifiable, sort of absolute measure of hallucination. If the LM spits out an object that isn't connected to that specific subject-predicate pair in that KG, then boom, by definition, it's a hallucination. Clean cut.
So they actually trained these decoder-only transformer LMs completely from scratch, just feeding them these KG triplets strung together. They added special tokens to mark the boundaries. And here's a really critical difference from how LMs are normally trained. Each unique piece of information, each triplet, was seen only once per training cycle, per epoch. This really unique setup allowed them to meticulously study how LMs might misrepresent their training data as they scaled up. Okay, now let's talk about scaling. Because, typically when we talk about LMs, the general rule of thumb has always been pretty straightforward. Bigger models, more data, usually means better performance.
Right, that's the standard wisdom, yeah.
But this research, it really uncovered some genuinely counterintuitive stuff when it comes to hallucinations specifically.
It really did. Now, if we look at the bigger picture, for a fixed amount of data, they did confirm that bigger models trained for longer do hallucinate less. So,
Yeah.
Okay, that's good news on the surface. However, the cost of getting to a really low hallucination rate, let's say 5% or less on data the model had seen, that cost was staggering. It needed an order of magnitude larger model. And as a result, an order of magnitude more compute than what you'd normally consider optimal for just general LM performance.
Wow.
It's incredibly, incredibly expensive, computationally speaking, to really stamp out those errors on known facts.
An order of magnitude.
Yeah.
That's a massive expense just to get them to reliably remember what they've already seen. But wait, it actually gets even stranger when you think about the data itself. Remember how they made sure each fact, each triplet in the KG was unique and only seen once per epoch? You'd think adding more and more distinct facts would just make the model smarter, more knowledgeable, wouldn't you?
You'd absolutely assume so.
Yeah.
That's the normal scaling law, right? Yeah. More data, better model. Yet, completely counter to what we usually see, increasing the data set size, so adding more unique facts, actually led to worse performance and a higher hallucination rate for any given model size and training time.
Seriously? Worse?
Yeah, worse. It seems like because each triplet was so unique and seen only once, it basically required direct memorization, like rote learning almost.
Yeah.
There was very little connection or, positive transfer between learning one fact and learning another. So just piling on more unique, disconnected facts actually increased the memorization burden without offering much leverage. It just made it harder.
That is a real head scratcher. More data leading to more hallucinations in this specific setup that really challenges the intuition. And they also sound something interesting about training time, right? Multi-epoch training.
Yes, absolutely essential here. Unlike a lot of modern LMs that might only be trained for one or maybe a few passes through the data, these KG trained models needed many epochs. We're talking 20 or even over 100 epochs, just for the hallucination rate to drop to what they considered an acceptable level on the data the model had already seen.
Okay, but training for that long, does that have downsides?
It does, and this points to another critical trade-off they observed. What's the consequence of all that training? Well, while it was necessary for memorizing and cutting down hallucinations on the seen data, they simultaneously saw the model getting worse at generalizing to unseen data, new facts it hadn't encountered.
Ah, overfitting.
Exactly. It's like that student who crams for a test by memorizing every single possible question and answer perfectly, but then completely falls apart if you ask them a slightly new question or rephrase something. So there's this clear tension. Train longer to nail down hallucinations on familiar stuff, but risk becoming less adaptable and worse on novel information.
Okay, one more thing on trying to reduce hallucinations. They tried adjusting the temperature when generating answers, right?
They did. So lowering the temperature, typically from 1.2 down to zero point 0, makes the model's outputs less random, more deterministic. And yes, doing that did reduce the hallucination rate. For the biggest models, it dropped from around 5% down to about 1.5%.
Okay, so that helps, but
Yep,
there's always a but, isn't there?
there usually is. In this case, the catch was that lowering the temperature also meant the model just generated fewer predictions overall, fewer objects. Its recall went down significantly.
Right.
It's a bit like someone becoming overly cautious. To avoid being wrong, they just stop making as many claims in the first place. An easy way to hallucinate less is simply to say less.
Okay, so we've established that getting rid of hallucinations completely is, well, incredibly hard and computationally very expensive. Which leads us to the next logical step the researchers took.
hmm
What about detecting them? Because even their biggest, best models still made mistakes, right? Still hallucinating around 5% on data they've seen.
And a whopping 50% on data they hadn't seen, so detection is still crucial.
Yeah, 50% is huge.
So they explored different kinds of detectors. Some tried to judge if a whole generated sentence or triplet was a hallucination. Others focused more narrowly. Was this specific word, this token, the hallucinated part? And they also played around with different ways of sort of hooking these detectors up to the main language model.
Now, intuitively, you'd think, okay, as the main LMs get better, bigger, more powerful, and they hallucinate less often, it should logically become easier to spot the mistakes they do still make, right? The errors should stand out more.
That would be the common sense assumption, wouldn't it? Fewer errors, maybe clearer signals when they do happen.
Exactly.
Well, prepare for another fascinating counterintuitive twist here.
Sure.
What they found was truly intriguing. While yes, bigger detectors generally worked better,
Wow.
and the sort of raw accuracy of the detectors tended to go up as the underlying LM got bigger,
Mm.
there was a critical catch. When they looked at a more robust metric one that really tells you how well you can find those rare errors without crying wolf all the time, a measure called Area Under the Precision Recall Curve, or AUC-PR. It's a better measure for these find the needle in the haystack problems.
Right.
They found a striking inverse relationship between the LM size and the detectability of its hallucinations using this AUC-PR metric.
Wait, hold on. Inverse relationship. So, bigger model.
Harder detection.
Let's really break this down because that sounds backwards. The more powerful the LM gets, the harder it becomes to detect its remaining mistakes.
Precisely. It's almost as if the smartest LMs are also the sneakiest. They get better at hiding their errors. And this is even when you have that perfect, controlled knowledge graph set up where you know exactly what the ground truth is.
Wow.
This finding really challenges the assumption that just having clean, controlled training data would be the silver bullet for making hallucination detectors work really well. Apparently not.
Okay, so let's try and pull this all together. What if we learn from this deep dive into the Google DeepMind paper? To recap, We started by looking at how tricky it is to even define a hallucination clearly,
Mm-hmm.
and how using a knowledge graph gave them this novel, quantifiable way to measure it.
Mm-hmm.
Then we got into some really surprising findings about scaling.
Mm-hmm.
We saw that getting hallucinations way down is incredibly compute intensive. It demands models much, much larger and trained much longer than we previously thought was optimal.
Huge cost, yeah.
And maybe the most counterintuitive bit
Mm.
for these KG models, just adding more unique facts could actually backfire and increase hallucinations.
Which is just wild when you think about typical scaling.
Right. And then, perhaps the most critical point we just discussed.
As the language models get more powerful and they hallucinate less often overall, their remaining hallucinations actually become harder to detect reliably.
It's not just a technical detail, is it?
No, I don't think so. It really speaks to the hidden complexities of building AI systems that we can genuinely trust. The smarter the model gets, maybe the more subtle its potential errors become, making them tougher to pinpoint.
So this really brings us to a final important question for you, the listener, to think about. If even in this perfectly controlled, highly structured environment, using a clean knowledge graph, if even there we face such significant costs and these fundamental challenges in both stamping out and even just detecting hallucinations, what does this really imply for the performance of LMs out in the wild?
Yeah, models trained on just vast, messy, often ambiguous, contradictory natural language data from the internet.
Exactly. How might future approaches need to adapt?
Yeah.
How do we deal with these inherent complexities, these trade-offs, to ensure we can actually achieve genuine factual reliability in the AI systems we're starting to rely on more and more every day, something to mull over?